Alrighty, so let's just chill and start a new project just to test this Minis Forum X1 AI Pro Mini PC. I've downloaded the Qwen 3 Coder 30B A3B Instruct model, and I'm serving it locally through LM Studio with a max, let me see, max context length here should be, in this case, 65,000 tokens, which is about 64K tokens. I've offloaded 36 layers to my 5090 with flash attention enabled. And what that gets me is about, with a simple high, 29.99 tokens per second. At this point, I've maxed out my resources. So my 5090 has 31 out of 30, about 32 gigs used. And I have no more memory left in my system. I'm recording, I have my terminal, a browser, OBS, and the model being served. So I'm just praying right now that I won't crash. You'll probably see a lot of SSD activity if I'm swapping. The only thing that I have plenty of right now is CPU and NPU, which whatever, I don't even know what is using this thing ever. So today, let's just do some local coding. So I set up, okay, so now I have the LM Studio server running. My server settings has it on port 8000. I'm serving it through the local network. And then I also have enabled everything else here, basically. Okay, now for Klein, I think I might need to configure this a little bit, but I think this doesn't work. I think I need to type the real IP, probably, but was it 35? 35 on my local area network. Yeah. So I've used an OpenAI compatible model with my IP, and then basically the model ID you can get from Elm Studio here. And definitely I've configured the model. I should probably uncheck this. I've configured the model to recognize it with 65,000 tokens and temperature of 0.3. And so yeah, that's it. If I just press high or type high to kind of warm it up, if I get a successful response in plan mode, we're good to go. NVTop is here to show basically power usage at this point. So it's a 600 watt card. I pray that I won't have like a circuit trip in this room. So it's 600 watts for the GPU, but only about like 100 or so watts for the computer itself. It's still a lot of power, that full power. Running nice and cool right now, relatively, for a GPU that's doing some work. The utilization is about 100% now, and it's actually going. So it's not quite as fast as running it on through my Epic servers. We've done Qwen 3 Coder before, but it should be good enough. And I'll introduce what the project is later. But notice here how the PCIe bandwidth is only at 4x, because that is because we are like at using Oculink, right? So Oculink is connected essentially to like an M.2 slot, you could imagine. Okay, I have tmux configured, and I've started a new project here. It's going to be interesting. So why don't I just start writing the design document, and then let's pass this design document to Klein so that it can vibe code for us, like using the Qwen 3 coder model. And so our design document is going to just outline what we want, and what we want is an emulator that interfaces with REST, or that exposes a REST API to control it. So what emulator? A Game Boy emulator that exposes a REST API to control the game, a playing game, a game ROM being played. Okay, so that's what we want to achieve. We want to create a Game Boy emulator because ultimate goal, play Pokemon, let's say red or blue, right? Using REST API calls to control the game and have a GUI navigation agent beat it. Okay, so like that's the ultimate goal. So let's do a quick introduction, right? Or purpose of the project. So purpose, a Game Boy emulator that exposes a REST API to control a ROM being played. So the ultimate goal is to play Pokemon red or blue using REST API calls to control the game and have a GUI navigation agent beat it, best it, beat it, okay? Or finish the game. Okay, so that's what we're trying to make here. And okay, now let's define some of the features that we want. So we want an emulator, a Game Boy emulator, which is implemented in the emulator directory. Okay, this is going to be a Python project. Okay, and we should keep it simple. We should keep the implementation simple and create a minimal emulator that emulates the following: the CPU, graphics, sound, and input. So we're not interested in emulating any other Game Boy peripherals. So we're not interested in emulating Game Boy peripherals. Okay. REST API, the server or service exposed to clients that can alternatively drive the emulator apart from just using, actually, you know what, let's just make a REST API the only mode of, yeah, REST API should be the only mode of input. So REST API service is allowed to be the only mode for input. So in this case, for example, JSON that tells, JSON payload that tells the emulator to invoke control inputs such as left, right, up, down, etc. Okay, so what else do we need? Well, graphics should still utilize some, or not should have Super Game Boy or color features. So what I mean by that was that the Game Boy itself had the ability to display some color. In this case, let's see, Game Boy Pokemon Red. In this case, like something like Pokemon Red had like minor support for some color. It's very basic, but I do like this feature. I don't like the having completely black and white. This is something that I want. So should support ROMs that had Super Game Boy or color features. Pokemon Red and Blue are examples. Okay. And now, yeah. So let's shoot this to the model. and then see what it comes up with, and then we can start designing from here with more technical features. But let's just have the model try to understand what we're trying to achieve. Okay, so in Klein, what I'm going to do is I'm going to just pass this design document. There we go. Design document. So design. This is a start of a design document for this project I want to create. So far, I have only written enough to help you understand what I am trying to achieve initially at a high level. I want you to read this and confirm with me whether you understand. Okay? So we want the model to understand stuff first. Then after that, we can dive in and write more details on the technical side together. Let's not rush. And models actually have this thing. It's like, so after we read, or after we have the model read our initial design, we're going to interact with it to develop more technical requirements. And after that, we need to think about things like in a way where we don't want to start coding right away, because models, they tend to want to like just generate and spit out code immediately. And this is actually more prominent with smaller language models, such as like the local ones, such as like Quen. So we need to be careful and mindful about that. And that's why I'm adding this type of language in the prompt. Okay, so now, let's see, after that, we can dive in and write more technical details on the technical side together. Let's try not to dive into coding so quickly and think it through together. I am a slow methodical thinker and planner. You should be the same. I am not a very good programmer, and so you should explain to me technical concepts in detail. Okay, so this is enough for now for it to get a start, and let's see what we come up with. So we have 65,000 tokens to make use of, but we can always compact it with Klein. And you see, we do have GPU activity. Notice how we don't ever really truly use our 600 watts because we're offloading a lot of these layers to the CPU. So the CPU is also working in addition when it's inferencing. So our GPU is never at like full load because of that. Yeah, I do need to order more RAM. This is scaring me because I do feel like there is slowness, and yeah, I just feel like I should be taking advantage of things more. Anyway, yeah, let's have it. Let's just read this. And you know what? I think we should make this font bigger. Let's see how we can make this font bigger. Klein font size, medium. I don't know what that is for. MCT display mode. Let's look for the features. So preferences, settings. Klein font size. Editor font size. No, that's just terminal, notebook, chat editor. Okay, so let's see if 16 does anything. So that's probably the editor. Chat is probably here. No, that's probably for Copilot. Okay, well, so sorry. It's gonna be a little small. Maybe I can just zoom in one. Yeah. I could probably do that and then reduce the font size in general. And that should get us to where we want to be. Okay, I'll reduce that to 18 to see what happens. And then the terminal font size I can make smaller too. Terminal font size. Ooh, let's enable font size ligature or font ligatures in terminal. Okay, cool. I think this is good enough. It's good enough. Okay. Shrink that a little bit. Okay, now we're good. So let's read what client says. I've reviewed the provided design.md content. Let me analyze what's been presented and think about what I understand so far. The project is a Game Boy emulator with specific goals. It should be implemented in Python, focus on core components, CPU graphics, sound input, no peripherals, expose a REST API to control ROMs being played, specifically target Pokemon Red Blue games, support Super Game Boy Color features, and okay, so I want them to do this. Confirm my understanding of the design document, then we'll work together on technical details. We don't want to dive into coding immediately, but think it through methodically. Let me make sure I understand all aspects correctly and then respond with a confirmation that shows what I've understood. So the main components seem to be an emulator core in Python implementing CPU graphics sound input, a REST API service for controlling the emulator via JSON payloads, support for Pokemon Red Blue ROM specifically, color support for Super Game Boy features. This seems like a substantial project and will require understanding of Game Boy hardware architecture and emulation concepts, Python programming with appropriate libraries, REST API development likely with Fast API, graphics rendering capabilities for the Game Boy for the emulator display. I should confirm my understanding to make sure I'm aligned with what they want before we proceed. Okay, so here we go. That was our thinking trace apparently, because this is an instruct model, so it's not thinking model. So thank you for sharing the design document. Let me confirm that I understand your project goals correctly. Project overview. You're planning to create a Game Boy emulator with these key features. Core emulation, okay, implemented in Python, focusing on CPU graphics, sound, and input components, excluding Game Boy peripherals. REST API interface, a service that exposes controls via JSON payloads to manage game inputs like left, right, up, down. Great. And a specific target, Pokemon Red, Blue ROMs with Super Game Boy Color support. And then technical direction, Python-based emulator implementation. Okay, great. REST API as a primary input method for controlling gameplay. Focus on core emulation components rather than full peripheral simulation. Emphasis on supporting color features from Super Game Boy, important for Pokemon games. Is my understanding correct? Yes. So I'll respond, yes, your understanding is correct. Okay, before we dive into technical details, I'd like to understand a bit more about your experience level. Oh, wow. This coin model is literally trying to get a gauge on how where I'm really at. Okay, let's do this. One, I do have some experience with Python programming. I know how to create virtual environments, install dependencies, and can create some scripts. Two. I don't have much experience with libraries like Pygame or TK Tinter, for example, but can pick it up very quickly with some documentation and your guidance. I'm just kind of like making it feel good too. Let's see. And now, emulator development concepts, if any. I know the basic concepts of emulator development, and this is why I want to do the video too. I kind of want to show like what a basic emulator would look like. I know about computer architecture, such as fetch, decode, execute, etc. That a CPU implementation could consist of understanding what opcodes to run and executing or writing code to simulate that, and that memory can be abstracted into an array. However, not much knowledge about graphics and sound. Okay? Now, 3 recipe design. I am very good at this. REST has been a good portion of my professional career. I can create web APIs. So I think this is a translatable skill. I have fun talking to these things. Okay, whether you have specific preferences for the Python libraries or frameworks, I just want to make sure that we create a very maintainable and debuggable projects, since we are essentially vibe coding, or actually we're not really vibe coding, but essentially creating something very complex and big. Simplicity is very important to me. But if we have to use multimedia libraries and game libraries, it is totally fine, and that's the whole point of learning. Okay, let's go. Let's see what this thing comes up with. Okay, how do I collapse this? I think I can just do this. Okay, cool. All right, let's read this. Perfect. Thank you for confirming and providing those details about your experience level. This helps me tailor my approach. Summary of your background. Well, you have Python, okay. Comfortable with virtual environments, dependencies, and scripting, a good foundation. Okay, thank you. Emulation concepts, understands CPU cycle basics, fetch, decode, execute, and memory abstraction. Yes, I do. REST APIs, professional experience. This is definitely a transferable skill. Oh, it's called transferable, not translatable. Okay, English. Project values, maintainability, debuggability, and simplicity are priorities. So next steps in our planning process. I love how it's telling me how to plan. This is like, I don't have to use my brain anymore. That's sad. Next steps. Since we're talking about a methodological approach, I like to propose that we now define the core architecture of how these components will interact, break down the technical challenges we'll face with graphics and sound emulation, identify key libraries and tools we might need, especially for GUI and graphics, establish a development roadmap with clear milestones. Let me outline what I think our approach should be, and we can discuss if this aligns with your thinking or if you'd like to adjust any aspects. Would you like me to proceed with outlining a technical architecture and component breakdown? Well, okay, so I would like that. I would like to start with outlining the technical architecture. However, would it also help if we documented at least the technical specifications and details of the Game Boy hardware itself? Or do you think that isn't very important here? So I think we should at least document that so that we understand what we're working with. So, okay, it also agrees with me. So, great question. I think we should definitely document some key Game Boy hardware specifications, since they're fundamental to our emulator design. However, let's approach this strategically. Ouch. My recommendation, start with a high-level architecture. Okay, so I actually want to go down too low right now for its taste. And I do agree, to the point, we should start with the high-level architecture first. That shows how components will interact. That's definitely true. We want to be able to draw out exactly what we're looking for. So then identify the essential Game Boy specs needed for our implementation. Focus on what we actually need to implement rather than diving into exhaustive hardware details. And so let me outline the core architecture first, and we can discuss which technical specifications are most important for our particular use case. So basically the REST API service here is going to be interfacing with the emulator core. Emulator core has CPU memory and graphics and display output. Okay, and then this is going through an input handler, which basically consists of logic that will fiddle around with memory, changing things around to update the state of the system. And then we also have a sound system that probably emits sounds at a specific sampling rate. So yeah, this looks about right. So this shows the main components and the relationships. The REST service would send commands to control inputs, which flow through our emulator core. So key Game Boy specifications we'll need. Since we're targeting Pokemon Red, Blue with Super Game Boy features, the most important specs include CPU, Nintendo Game Boy's custom 8-bit processor. Okay, that's like, I think that was like a Z80. Memory layout, how memory is organized and mapped. Graphics, LCD display specifications like tile formats and sprites. Sound, the audio processing unit specifications for audio output. Input, controller interface details. Would you like me to proceed with outlining the architecture in more detail first, or would you prefer we start with the specific Game Boy hardware specs that are most relevant to our goals? Actually, let me update the document with a mermaid diagram of the high-level architecture, and then you tell me what you agree with. Give me a second to do that, please. Okay, so here's like another application, I guess, of what we can use local AI for. What I'm going to do is I'm going to draw a diagram. I don't know Mermaid very well. In fact, I don't know any at all. The only Mermaid diagram experience I have is that I just fiddle around with whatever an LLM generates. I actually don't conceptually understand. I mean, I'm pretty sure that if I tried I put some effort to learn, it's no problem. But so here's the thing, like, I think philosophically, right? So like a lot of programmers that are starting to program today with a lot of AI, they probably don't understand fundamentally at a very deep level how code really works, or at least how code executes with the computer. So similar with me, like I'm learning a lot of things. Oh, sorry, but they are able to do like really, really cool things because the AI is helping them. But it's not like they don't know how to code. It's just that, like they have a lot of assistance, so you don't really need to care about like the nitty-gritty details. So yeah, again, like same for me, right? Like I only started caring about like diagramming, mermaid diagramming, and writing more and more documentation because life has gotten easier when it comes to that with LLMs. And so I've learned the mermaid documentation or mermaid diagrams very late, where I had access to AI. And because of that, I know what mermaid diagrams are. I know like how to fiddle around with them to get to what I want, but I personally don't know how they really like I don't have the ability to write one from scratch because I've never sat down and read everything about it. I'm sure if AI wasn't here, I would have done that. But yeah, I mean, you can't learn everything. You could, but you want to do other things too, right? So yeah, what we need to do is we need to get a vision language model. So how we're going to do this is we're going to download a vision language model, and then we're going to draw a mermaid diagram, or like draw a diagram here, and we're going to see if we can pass that to a vision language model, can it create a mermaid diagram for us? So like we're really using AI here as like we have like multiple assistants, right? So in this case, I think we can use one of these vision language models. So I'll search for Qwen3VL and see what's a good one to pick. I really like Unsloth stuff because they usually have, again, I said it before, like bug fixes and things like that they've probably implemented. I do like thinking for this type of work because it does need to like see what's going on. And a 30 billion parameter model with 3 billion active parameters is pretty good. But also, I really like the 32B model because it's big and substantial and smart enough to do like almost the toughest things I throw at it. And we can run this offloaded too for like with CPU and GPU. I want to get the Q8 KXL model because I could run it. It's gonna take about 42 gigs of total memory. I have 32 gigs here, 32 gigs here. That's 64. We'll barely squeeze. We don't need a lot of context because we're not having a back and forth conversation. We're just doing a one shot thing. So I would say this could probably suffice for just like one mermaid diagram. So I'm going to download that. But as I am doing this, I'm starting to realize that I might need more memory. So here's how I would go about upgrading memory. The first thing I would like to do when I want to buy memory is I need to understand what memory speed do I need to buy, and do I even have the ability to upgrade memory. I'm more concerned about RAM because I can't get anything better right now than a RTX 5090 for this thing. So I know I keep saying this because I'm like bragging, but I'm so sorry. So, but the one thing I could like upgrade here is memory. I can, because I'm okay with this token speed actually with these smaller language models, about 30 tokens per second. That's like way more than enough for me. I'm pretty slow when it comes to coding and doing work. So for me, it's enough. So yeah, apparently Windows reports this as 5600 mega transfers per second RAM, and I think slots means that I do have slotted memory, SODIMM. Okay, so I could put 2 sticks. So most likely I want to buy 2 sticks of whatever higher capacity than this thing here. And so I really want to confirm that. If I look for minis forum X1 AI Pro, looking at the product page, I think it does specify technical specifications. Okay, so yeah, 2 SODIMM slots, DDR5 5600. So man, this is a great product page. Let's see, Copilot Plus, Oculink. Yeah, I bought this machine just for this. It's amazing so far. It's been very stable. It's more stable than Thunderbolt, that's for sure. And a built-in power supply. There's no power brick at all for this thing. It's beautiful. Okay, so yeah, it is a DDR5 5600 mega transfers. So I know that we should not be getting 2 sticks of 16. We should probably be getting at least 2 sticks of 32, or actually 2 sticks of 48 is also an option. Let me just make sure this thing is still downloading, so I'm not just talking. Okay. Yeah, so let's go to BH Photo. BH Photo, yeah, and just like check out like prices. So we can look at what am I supposed to look for? Computer components, and let's look for computer memory, and we want to filter by SODIMM. So is there anything we can use here? Okay, so DDR5 is what? SODIMM? We can just check all the SODIMMs, right? And that'll be okay. Sounds about right. Okay. We'll check all that. And then capacity, we really don't want anything under 32 gigs, so we'll take 48 gigs, either 1 stick or 2 by 24, or 1 stick of 64, 2 sticks of 32. We don't want 4. Ooh, got a nice 6. And if we're feeling really baller, let's do 128. Let's just check the prices. I know RAM prices have been increasing like crazy lately. I think this is actually a very expensive price. So let's filter to DDR5 5600 because that's what our computer uses. And then let's also can we sort by low to high? Okay, cool. So in fact, let's get rid of all the single sticks because we want to go dual channel right away. That's like the recommended thing is to just buy RAM in the same kit, so we don't have any sketch things happening with the computer. And so yeah, obviously this one's out of stock, so that sucks. I like Crucial. I don't even know if Silicon Power is a good brand, but PNY is a good brand too. We can go 2x48, but I feel like that's not like a huge upgrade because I actually am very tight right now, and even though I'm not writing to swap, I do feel like I feel very limited basically, and I think I've already unloaded the model too, and yet I'm still using 60. Am I? If I have no, I'm not. I'm still using the model, so I still don't have like room, right? With context, I'm limited to like 64,000 context for at least this coding model, and it's actually quantized too. So I want to actually go higher. I want to go to at least 64 gigabytes of memory. 96 is an option too with $406, and then you finally have the 128 gigabyte kit, which I'm so tempted. I'm very tempted to get. But let's do some math. Okay, so we have let's just take these three. Even though like this is PNY, I think they're about the same price. Oh, actually this one's cheaper, but PNY must be good. So like all the NVIDIA stuff is made there. So 336 divided by 64 gigs. So that gets us about $5 a gigabyte, 5.25. So 5.25, and then we'll have $407 divided by 96. That's actually $4.24 a gigabyte. And then the 128 gigabyte stick is $595 divided by 128, and that's $4.64, or it's $4.65. So let's assume that we can get this kit here for $314. What we get? So 314 divided by 64. Okay, $4.90. So this is like $4.90. This is like $4.24, and then this one is $4.65 or whatever it was. Obviously, then you get more bang for the buck if you go higher. The sweet spot is 96 gigs. I'm really tempted for the 128 gig. So let's check out. Am I done downloading it? Okay, we're almost there. Okay, so let's check out. Just check out the prices. Okay, so Amazon has, oh, this is not it. Let's search for Sodin. Okay, so Amazon, let's see here. There's no 128 gig kit apparently. Okay, well, Amazon doesn't have it. Should we do 128? Yeah, definitely Amazon does not have it. We have this Nemix one, which probably is not a good brand. So we also have Micro Center, but whatever, it can't, it's impossible. Sodin. This is Sodin. Okay. So it's actually pretty hard to find these things. Let's do shopping. So, okay, this is a lot. We can try Newegg. Let's go Newegg and then see the equivalent kit. Whoa, what's going on here? Okay, Black November. Okay. Okay, Sorry, this is a tangent. Whoa, that is expensive. Is that real? My goodness. Wow. Is this the same kit? What? That is robbery. CTK, CTK, CT2K64G. CT2K64G56C, 56C, 46S5. Wow. Okay. Oh, well, a crest, temporary out of stock. No wonder. That was too good. This is too good to be true. Wow. Okay. Well, this is out of after. Okay. No. We're not. We're not gonna buy this for $1,365. Welp. This is also out of stock too, so I wasn't even checking. I guess this is the best option we have. Oh man, RAM is expensive. Let's check Newegg. The 96. Maybe this is just them trolling. Maybe. Okay, this is more reasonable. It's more expensive than B&H, but yeah, looks like we might have to get 96 instead. Yeah, I'm going to do that offline after this. After this recording. Okay, nice tangent. Alrighty, let's eject this model. We're done here. Let's load up this model and then use LM Studio to help us generate a mermaid diagram. So in this case, I think we might need at least 32K context. We can enable flash attention to lower our memory usage, and then can we just crank this up to maybe 40 layers offloaded? And I think that's pretty good. We do have enough GPU memory, so 30 gigs, 32K context, because it's going to start thinking like crazy, and then who knows, this mermaid diagram might be big. So let's load our model, and then go to Excalidraw and draw our diagram. I don't even know if we can translate this to mermaid, but let's do our best here. So we have a REST API. Let's start over. Okay. So we have a REST API. Okay. And then the REST API is going to be receiving stuff from user. Okay. REST API is going to then control the emulator. So let's say Game Boy. I actually don't like. I want to be clear. That's why. Let's do Game Boy emulator. So this is basically it, right? Like, so then this, and then the emulator is basically containing the ROM, and that's the flow, right? But within this emulator, I'm just like sketching out right now. Within this emulator, what do we have here? Like, we'll have, so make it neater. Game Boy emulator. Oops. Okay, what do we have here? We have basically the CPU. We have the memory. We'll have the sound, and then we have graphics. Okay, and then we'll have input. Okay, so here we can say CPU. This one here will be memory. This one here will be graphics. This one here will be what is it, sound, and then input handling. Okay, so here now is basically the REST API. I should have just done this to begin with. REST API. And then the REST API will just go to input handling. And then this will be client. And then we can just get rid of all this. I'm just like doing this on the fly. So get rid of that. So client, REST API, input handling. And then CPU is interfacing with memory. And then I think, what was it? Memory interfaces with graphics. And then we have sound and input handling. Input handling is also probably going to mess around with memory. Let's just do that. Okay. Okay, simple. So let's just see what it comes up with. Okay, so let's just take this and let's throw that in here. And then I want you, oops, caps lock's on. I want you to help me convert this very high level diagram of Game Boy emulator that is able to be controlled through REST API to play games into a mermaid diagram. At the same time, please give critique whether this architecturally makes sense. I know this is like a lot of effort for something simple, but then like I want to just like kind of just demonstrate a flow and how we can get stuff done with LLMs in this case. So it is going to be slower. It's a 32 billion parameter model. Yeah, it's and it's offloaded with to CPU when I'm sure like if this was purely on GPU, it'll be so much faster. So right now it looks like it's still processing, so it's probably gonna take a while since the CPU is a lagger here. What's interesting is that I feel like this is taking way longer than it should, but maybe it's because this picture is really big. I am on a 4K monitor, but I have 200% scaling. I don't know if that makes a difference, but we'll see. Okay, so finally it's thinking. It is this slow because I have to do a lot of CPU inferencing on memory because I can't fit everything into GPU. But that's totally fine. I have enough context. I'm willing to wait, and just looking at his thinking trace, it's fine. So I'll just let this run for a bit longer, and then we'll check back on it. So it's done outputting something. Apparently it did give us a mermaid diagram, so that's good. But I also asked it to give me critique, and the reason why I did this is because we didn't put that much thought into creating this diagram, so for sure we didn't think a lot of things through. And I just want to go over this so that we can make some improvements or decide whether or not we can just punt and continue on with the project. So let's first take a look at least what this model Qwen 3VL32B outputted, and we'll just dump this into, we'll dump this to our README. That's a preview. There we go. And let's see if this actually gets updated with the flow chart. Let's see. So tick, 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 mermaid, tick, tick, tick. Okay. And we have something here. So I'm going to tuck this aside and we'll see what we generate. So client interacts with the REST API, input handling. I guess this is kind of right. Input handling will take in the payload, and then that updates memory. CPU then invokes instructions. Whatever is in the memory here. So let's say like joypad hits like the A button, for example. A button will then do something in memory. CPU in a specific cycle will pick that up. And then graphics is probably interacting with memory and memory mapped wise. And then sound, we still don't really know yet. But yeah, this looks about the general approach, what we were trying to communicate. But again, very surface level. So let's see what Qwen3VL32B wants to help us out with. So architectural critique strengths: clear component separation. The internal emulator components, CPU, memory, etc. are logically grouped and show proper data flow. API abstraction. REST API as a control layer provides clean separation between client and core emulation logic. But we have critical issues. Oh no. Critical issues. REST for real-time gaming is problematic. Well, no, because we weren't clear that what we want to have it play is basically a Pokemon game, and Pokemon is quite slow. In fact, nothing really updates unless you actually perform some sort of action with like a confirmation for a dialogue or selecting a menu item. These things actually progress the game, so it's not like we're looking for real time. So let's clarify. Okay, so to address your critical issues concerns, ROMs that will be played by the emulator will not need real-time communications. They will just be things like, they will just be JRPGs like Pokemon Red or Blue, for example. Okay, so that's thing here. Missing output path. Diagram only shows input flow. Client API emulator. No mechanism shown for sending rendered frames back to client. Okay, so rendered frames are rendered back to client for sure. Thanks for the call out. Okay. How does the client see the game? That's a fundamental requirement. Okay, client sees game as a desktop app. The REST API service is on the same machine and not the web. Okay, so I think it thinks that we're going to deploy this on the web. Scalability concerns. REST API will become bottleneck for multiple concurrent clients. No, only one client is running this service. It is not web scale, but for a desktop service. Okay. Next would be input handling design flaw. Input should be processed in the emulator's timing context during CPU cycle. Okay, that's true. Current design shows REST API directly feeding inputs into a separate component. Input may get processed out of sync with the game state. So this is kind of like, I would say, up in the air because I don't understand the Game Boy architecture. I at least I know with like the NES, input handling is kind of separate from CPU, and that there's like polling involved that the CPU does every once in a while to grab input. Okay, recommended improvements: add output path. Fair. Replace REST with WebSockets. No. Add state management. Too complicated. Add error handling. No. no. We're not that type of application, and yeah, this is very high level. So this is a good high level concept, but fundamentally flawed for actual implementation. Okay, the architecture would work for non-real-time use cases. Yes, so again, this is for non-real-time, real-time purposes, and also not for web scale. Here, I agree. The chart should indicate some output path. Let's leave the input handling at least up in the air for now, since I don't yet fully understand Game Boy architecture. And then let's also keep it simple. Remember, this is high level. We worry about synchronization, queuing, and output streaming, error handling, etc. later. We just care about component architecture. Please just make edits in the mermaid diagram to include some direction of output, nothing else. Okay, so we'll do that, and then it'll come back to us with some sort of response. So the last response took about, well, it thought for 8 minutes, and then this one took this one outputted 2.238 tokens total with 3 tokens per second, and it is pretty slow. Yeah, so apparently I have clarifications that change everything in its perspective, so that's okay. Yeah, so let's wait for this thing to finish, and in the meantime, I'm going to figure out my RAM situation and see if I can order at least more RAM, and maybe install it sometime this week if it comes. I need to find a good price. So I'm thinking about getting the 2x48 kit or the 2x32 kit. There's no way I'm going to spend money on or at least overspend on 128 gigs. So that's out of the question, especially with how expensive RAM prices are nowadays. So let's just check at Newegg how much this is. Okay, so here is this RAM. So it's $419. That's not bad at all. I could definitely just order this from Newegg. I don't think it's from Newegg directly though. It's from 3C Expert. They seem good. So with 17,000 ratings. So I think this makes sense to me. It is a good amount of RAM. 96 gigs is pretty much going to be 3 times as much as we have right now. The scope, like the size of the models, I'm only really interested in running on this workstation would be the 30 billion type parameter models, and it seems to be good enough for me. If I need anything more, that's where we're going to try to offload things to the DGX Spark, even though it's going to be slower. We haven't really exercised the full power of the 5090 yet because we've just been offloading things to CPU and it's pretty slow. The reason why, let's say, this model seems to be slower is because it is a dense model, so it's all 32 billion parameters active on every token generation, versus when we were on the Qwen 3 coder model. I accidentally tried to send a message earlier, but this is a mixture of exerts model, so meaning that of the 30 billion parameters it has, only about 3 billion parameters are active per token generation. So this is why this one feels very fast and tolerable, while this one here is a much bigger model overall, and so that's why it's like 3 tokens per second versus 30 tokens per second in this case. But this is not too bad. I mean, I've already talked my way through to to having it output something. And I think this is going to be the one that we're probably going to use. So I'm going to just copy this and I'm going to paste it into here and we'll see. Okay, cool. So rendered frame, we'll just go back to the client and I think that's good enough for now. So let's actually delete this because I had this message here to just put this in. But I don't think we need it anymore. So let's hope it just goes away. Okay, let's send this in context and say, okay, we here is a mermaid diagram that is placed into at design.md. Tell me what you think. Are we aligned? Okay, and this one is fine now. It looks like it agrees with everything we say. So I'm going to eject this model and I'm going to go back here into server settings and I'm going to load the 30B instruct. Just going to load it back so that we can access it from client again. Yeah, we're just gonna do some model switching, and I think like maybe I could have gotten away with using a smaller vision language model to read in that diagram. Who knows? Maybe we'll try that next time. We'll use the 8 billion parameter model and see how that goes. Maybe next time we could try that at full precision rather than a quantized version. I think I had tried quantized 8-bit quantized in this case. Okay, so we're back and now let's send a message and see what happens. So we'll send a message. So we will cancel this API request, cancel that. I want to send this one instead. And then let's see if it's aligned with what we're saying. Of course, in the beginning, API requests are going to take a long time with client if you've shut down your server because of the caching is gone. But this one is not too bad. It should just come up pretty quickly. In this case, if you look at the LM Studio here, it's already processing the prompt. Yeah, at a good rate, about 3% each time it updates for every, I guess, second in this case. Yeah, every 2 seconds. So in this case, we're looking at maybe 30 more seconds for us to start receiving a response, and should happen right about now. Okay, so generate some tokens for me. Hello. Uh-oh. Is not doing it? Is it doing it? Is it doing it? Okay, so great. It was absolutely struggling to do that. So thank you for sharing the updated design.md with the mermaid diagram. I think we're well aligned on the architecture. Let me review what we've established. Architecture review. Your diagram shows a clean, logical flow. Client, REST API, input handling. Inside the Game Boy emulator subgraph, we have CPU memory graphics. Input handling feeds back into memory. Graphics outputs rendered frames in the client. So what I agree with, separations of concern is good. REST API is an interface layer. Core emulator components are properly identified. CPU memory sound and graphics input data flow makes sense. Sure. CPU executes instructions to access memory, which drives graphics output. Yeah, it's true because the graphics could be using the CPU memory for its memory. Suggestions for further clarification. We might also want to consider where sound fits in the data flow. Does it also feed into memory or operate independently? The client receives being rendered frames suggests we'll need some kind of display output mechanism. For Pokemon Red Blue specifically, we should ensure our graphics implementation supports Super Game Boy Color features. So next step, I think we're ready to move forward with more detailed technical specifications for the components. Would you like me to propose specific technical details for each component, CPU, memory, graphics, or discuss what Python libraries might be most appropriate, outline how we'll handle REST API integration, or prefer to take a different approach? Okay, so actually I want to do this. Wait, cancel. I want you to do something else right now. Let's edit the design.md to indicate that when we mean REST API service, we are not speaking of web scale. We are interested in only using it as an interface for an AI model to agent to interface with. So there is just one user, no concurrent considerations, and we do not need to worry about network latency and synchronization issues. Also clarify that we are not interested in real-time processing. Rather, the games that we are most interested in playing are pretty slow and progress made only through invoking actions, not like a shooter or a platformer. Okay, can you make these edits into the design.md file so that we can remember these details? Okay. And I'm on the act mode now, so it should autonomously edit everything that that I've already communicated to do. Okay, so it's doing it right now. Let's see what it does. I hope it doesn't go off and start like doing technical writing, because that I want to save for like a different phase. Okay, so service context. The REST API service is intended solely as an interface for a single AI agent, not as a web scale service. There are no concurrent users or network latency concerns. Great. That's it. Yeah, that's what I want. That's what I want. Nice and simple. Thank you. Okay. Now the clarification about the non-real-time processing nature of the games we're targeting. Okay. What's it going to do here? All right. Clarifications on that should be coming soon. Okay, so processing model. The target games like Pokemon Red, Blue progress slowly through discrete actions rather than real-time interactions. The emulator does not need to process at high frame rates or handle concurrent timing requirements. Great. Okay, keep going. Now you can imagine that if we could fit everything in memory, or at least VRAM, it would be so much faster. Okay, so he's done, or she's done, or it's done. Now, what we need to do is we need to probably get a PDF or some sort of the Game Boy technical specifications and have it understand it in context and summarize it so that it can be placed in here. So far, we've used 20.8K tokens out of 64K, so we're in good shape. Let's search the internet for some Game Boy specifications. Okay, so we have this website here that has a lot of details on Game Boy stuff. I think it's for Game Boy development, but this is very good. This has a lot of details. And so I think we should get a single page version first of all. So it's gonna be really big. Okay, so there's a lot of context. And I wonder whether or not the AI can maintain all of this. This will be interesting. So what I want to do is I want to print this as PDF, and let's see what we get as our PDF. I hope it's readable. In this case, it looks like it is. Yeah, it looks like it is. So let's just get all of this, and this is a very large document. It's like 286. Let's do this. Let's blow our context window. And I wonder if Klein can chop this up for us. We'll see. Let's print this to PDF, and let's call this Game Boy documentation. In fact, let's put it into our whistle. So whistle.localhost/ubuntu, and let's throw it into our code repo. How are we going to do this? Let's save this as Game Boy documentation. And I'm thinking here that either we use a smaller model or we can just store it all in here. Let's do this. Let's compact our context first and see what happens. So compact tasks, and let's just see if we can reduce the context so that we have more. So no. I don't know. Wait, this is not what we want. We wanted to compact the context. What is this? Okay. Well, let's do this. Let's attach, in this case, some documentation. So here is some documentation about the Game Boy itself. Now I want you to go through this document and see what is useful to be placed into our design doc, and see what you can learn about the Game Boy to help us with our emulator. Okay, this could be bad idea. If it's a bad idea, we'll find out some solution. In fact, let's see. It appears to be corrupted or unreadable. Oh, nice. It wants to search for a directory. How is this corrupted? It appears to be corrupted or unreadable. Why is that? I guess I never checked it. So, let's see here. It is 26 megs. It's big. No, I want to test RAG capability. That's why. Okay, let's unload this, and then let's use something that is very good for summarization and loves to output tables. Let's use GPT-OSS20B. Let's do that. Yeah, let's do that. So let's eject, and then let's add a new chat. Let's use GPT-OSS, maximum context, maximum GPU offload, and let's do this. Let's load that up, and then we have RAG. We also have what other things that we have. Install what? It's okay. Okay.
Attach files. There's no limit. Oh, combined size of 30 megs. We're perfect, perfect, perfect. Okay, so we can fit it all. That's great. I was just trying this out. Using AI to write an emulator because I don't know how. Maximum size per conversation, cannot add files. How is this? Is 26 megs though.
Maximum file size per conversation reach cannot add. But that's okay. Yeah, I don't think RAG or PDF summarization is going to work. The files are too big, and I'd have to split the entire documentation into separate PDF files, which I don't think it's worth it because by then I should just spend the time to read over this and yeah, I mean, what's the point of having content if I'm not going to talk about anything interesting? And so, yeah, this is going to be programming now, programming with AI and just trying to create something useful. If you don't like it, you can just not watch this video, especially since it is getting kind of long and it is already the next day. I decided that I needed to move on and yeah, just go on with my day. But I'm back now and I've decided, okay, well, there's no point in doing this if I'm not going to learn anything. So I'm going to learn something. Anyway, let's just start out by looking at the specifications of the Game Boy. So if anyone doesn't know what a Game Boy is, Game Boy looks like this, the original Game Boy, this one right here. So this is the original Game Boy. And here we go. Yeah, there we go. This is the original Game Boy. It came out in 1989, and I think one of the first games was Tetris. But I think what really holds near and dear to me in my heart is Pokemon Red and Pokemon Blue on the Game Boy. I actually played it on not the original Game Boy, but I played it on the Game Boy Pocket. And the Game Boy Pocket, this one. Yeah, this one. This one was a refresh of the regular Game Boy sometime in the 90s, and it's smaller, and I think had better battery life. Yeah, it's just two smaller AAA batteries, and 10 hours of gameplay still. Still a crappy screen. You still can't really see anything when, especially when it got bright. But it was a good. It was a good thing to kill time with. Anyway, so Game Boy Pocket and Game Boy are pretty much the same machine. It's just that I think the Game Boy Pocket had more modern hardware, but still equivalent. I think it's just like a smaller 8080 transistors. So we're still the same, but it was like we call it process node, right? So anyway, so the CPU here is an 8080. So that's kind of like the predecessor to the x86 CPU. So it's 8 bits. And it runs at 4 megahertz, 4.19 megahertz. And that's really important because it means that we're doing 4 million operations every single second. And when we're writing emulators, we have to keep track of this. And system clock is 1/4 the frequency of this master clock. We'll figure out what that is later. And then the Game Boy, Game Boy Pocket, and the Super Game Boy all only have 8 kilobytes of RAM. And VRAM is 8 kilobytes itself too. LCD is the physical screen type, but that doesn't really tell us anything. What we really want to know is resolution. So the resolution of the Game Boy and the Game Boy Pocket are 160 by 144 pixels, and that means that in our emulator, we're going to have a frame buffer that's around this big to store all these pixels. That's actually not that big. If you think about it, 160 by 144. Oops. That's only 23,000 pixels on the screen. So very primitive hardware. Sprites,
each sprite can be 8 by 8 or 8 by 16 with a max of only 40 per screen and 10 rendered per line. So when we say 10 rendered per line, what that means is, say you have a screen. Okay, so for example, let's take a screen here. Screen. Okay. And back in the day, you had, this is like a CRT screen. Or, yeah, this pretends like a CRT screen. You rendered things line by line, right? It means that for every line, you can only have 10 objects here. But in total, you can only have, in this entire screen, you can only have 40 objects. Okay? But in each line, you only have 10. So you can have like maybe some here, but they're not on the same line. Maybe some over here. And that's the reason why, like, it's like, you don't want to keep, you don't want to render too many in one line, because then that requires a lot of processing power in this case. So 40 objects total on the screen, but only 10 can occur at the same time per line, that's what they're saying here. And so palettes, we can have, I guess, one background palette, and then 4 different, or actually one background palette with maybe 4 variations, and two palettes with 3 variations, 4 shades of green and 4 shades of gray for the Game Boy Pocket. So funny enough, the regular Game Boy operates on monochrome, but it's like green rather than gray. Horizontal sync, 9 kilohertz. Vertical sync is 59, so that's like 60 hertz, really. It's NTSC. That's like VSync. 4 channels of sound, so 4 like square waves, bleeps and bloops, and takes about 0.7 watts. Okay, so let's summarize this, and we'll see that you see here that the Super Game Boy is essentially the same. It just has a 256 by 224 border. That's about it, really, and 32,000 colors. So how are we going to arrange this? Well, what we can do is everything stays the same up until color. And I think in colors we can just make an exception. I have no idea what this complicated mean, but let's just assume that it's 9 and 60, because even the Game Boy Color is the same. I think the reason why it's complicated is because it just depends on the TV, because the Super Game Boy was meant to be rendered onto the TV and not on the device itself, powered by the SNES. Okay, so let's summarize that in our design document, and let's start a technical specification. So Game Boy hardware. So we have technical specifications. And let's have this. Here are the technical specifications of the Game Boy hardware. So this is basically reflecting what we are going to have to emulate, like each of these components. So let's create like a markdown table. CPU, okay. Or actually let's do Game Boy. Super Game Boy. In case if we need it. Okay. Okay, so now let's do this. Let's just have, let's see, component as a column, and then a Game Boy, and then a Super Game Boy. There we go. That looks okay. CPU. Game Boy will be 8-bit. 8080 Sharp CPU. Maybe an SM83 core. Okay, and then 8-bit, or let's have this be the same. So 8-bit 8080 Sharp CPU, SM83 core. Okay, next one will be clock. Let's just put clock as 4.194 megahertz, and then same thing for Super Game Boy. You know, in fact, let's forget about Super Game Boy and just let's just do one thing and get it right. So let's do it this way and just get rid of this just to save some time. So system master clock and then system clock is going to be 1/4 of the master clock. Next is RAM. That's 8 kilobytes. We have VRAM or video RAM. That's also 8 kilobytes. So kilobytes is basically 1024 bytes times 8. That's what kilobytes are, not 1000. Kilobytes would be 1000 in this case. Screen. We don't really need to care. Well, let's just do resolution instead. 160 pixels by 144 pixels. And then object sprites. We'll have BG 1/4, and then objects 2/3. We'll figure out what that is later. Oh, sorry, that's palette. Color palette, and then object sprites. Let's say they are 8x8 or 8x16 pixels. Max 40 per screen or 10 per line. And let's have a colon right here so that we don't get confused. Color palettes and then colors. 4 shades of green. Horizontal sync is 9.198 kilohertz. And then vertical sync is going to be, let's be precise, 59.73 hertz. And then sound, 4 channels with stereo output. Okay, so rendering that, it looks about, yeah, it looks like what we want here. And let's have the LLM acknowledge this technical specification. So we can throw that here and say, here are the technical specifications of the Game Boy hardware for your knowledge. Okay, so now that we have that, let's go on next to memory map. Okay, so it's important to understand the memory map of the Game Boy, because how it works is that everything is written to address space of from 0000 to FFFF, and if this is 8 bits right here and this is 8 bits, it means that the Game Boy has a 16-bit address bus. Okay, now this entire memory map here is used not only for game memory, but also for video memory and also other parts from the cartridge, and then IO. Okay, so even though, like, okay, so if you think about it, 16 bits, right? What's 2 to the 16 here? 2 to the 16 is, how do I do 2 to the 16? Can I do exponent? We had to change it to standard scientific, maybe. 2 to the 16. Yeah, there we go. So that gives us about 64 kilobytes, right? So when we have 64 kilobytes, we have basically 65,536 different addresses. But our work RAM here is only 8 kilobytes, so that's about 8,192 addresses. With video RAM, another 8,192. So we have many more memory addresses we can make use of in this address space, which is why we're using it for other things too. So think about it this way, is that the computer, in this case the Game Boy, interfaces with all its hardware, cartridge, everything through memory addresses, virtually. Okay, so whether or not it's actually in real RAM, it just depends on the memory address it tries to access. So for example, this is internal RAM right here from the system. If the CPU is accessing any address between C0000 CFFF, it means that it wants to access something in its real memory. But if it's trying to access something in 8000 to 9FFF, it means that it's trying to mess around with video memory. And pretend, I'm not exactly sure yet, but this probably corresponds to like the joystick, the control pad, for instance, right? So FF000, FF00, and FF7F, if it's trying to access like read or write to these addresses, it means that it wants to do something with controller input. And here's actually more detail on exactly what each of these addresses do in this range here. So yeah, so it does have to do with joypad input. So FF00, depending on what's in there, corresponds to most likely what button is currently being pressed. Okay, so the data in here probably contains the information about the current button being pressed, and then you have all these other things here. Video by itself, okay, normal RAM may be used as such. Okay, so the PPU interprets it in specific ways. So bank 1 does not exist except on Game Boy Color. I guess it's on CGB Color. What's CGB mode? Let's see. CGB mode. CGB mode. What is CGB mode? Color mode. Okay, color mode. Cool. So we do have mechanisms to make it be aware of some color. That's good. But let's come back to that later. Let's like just slowly, just take it, just enjoy ourselves, and just slowly learn about the Game Boy hardware. Okay, so let's stop right here for now and read the response on what the AI thinks about what we've written so far. So I've now reviewed the updated design MD file, which includes technical specifications for the Game Boy hardware. This is very helpful information for our implementation. With these technical details, I can refine my implementation plan. Okay, so it still wants to set up project structure. So I disagree with that. Let's just keep writing technical specs, because I'll just tell you this. I actually started a new chat here, and I just had to write this paragraph here along with this markdown file to get it up to speed on everything. And it saved me a lot of time from having to reiterate myself. So that's like a power user tip right there. And that's the reason why I'm investing so much in just writing things down so that it can understand what is going on, saving you a lot of time later down the line. So it does understand what we've written here. It's like, this is exactly what is in our document here. And yeah, so it's still wanting to do, it wants to get ahead, right? So I don't think it's the right time to do that yet. I think what we need to do is, okay, so let's first implement the CPU. Now that we know more, it's an 8080 CPU, and we know that there is memory here. We can just probably like create the CPU and create like the memory map, and then we can go from there. So CPU specifications. So CPU registers, right? So every CPU has a bunch of registers. In this case, the not Z80, I keep saying Z80. This 8080 CPU has 1, 2, 3, 4, 5, 6 registers. Stack pointer and the program counter here are the special registers that's going to help keep track of how the program is running and where it is in memory, specifically in terms of its code segment. And then A, B, D, and HL are general purpose registers where you can just use to manipulate and do calculations. Now, the flags register. So flags register is a common thing in CPUs. They basically, but depending on the position of the on bits, like you have like let's say you have like a 8-bit number, so an 8-bit number, and that's represented by zeros and ones, right? So 0 1 1 1 0 0. Okay, so this is what we considered on, and this is what we considered off. So 0 means off, 1 means on. Depending on which bit within this 8-bit number is on or off, that tells us by position, what type of flag is currently set. So in this case, maybe this could be a flag that tells us whether or not our result in another register is 0, or this one can tell us whether or not something is a positive or negative number, right? And so we would have to just check these individual bits to tell the state of the world in our CPU. Now, as it turns out, with the Game Boy, we only need 4 bits to determine the state of the world, whether or not the result that was just computed is a 0, whether or not, I guess, we have subtraction, like overflow maybe, and then whether or not we carried one end of the number and versus maybe at the end of the entire number here. We'll see. But basically, the important thing to know is that we have a flags register, but it's only the lower 8 bits of our AF register here. Okay, it looks like it's 4 bits. I don't know why. There should be way more than that, but it's basically the lower. So bits 7, 6, 5, 4. No clue what 3, 2, 1, and 0 are. Let's just keep reading. But AF's lower bits, you can interpret them as flags, and then maybe the upper bits or together is the full number itself. So okay. So the carry flag. So 0 flag is obvious, right? 0 flags is set only if the result of an operation is 0, used by conditional jumps. The carry flag, it's set when the result of an 8-bit addition is higher than basically 255, and then the result of a 16-bit addition is higher than 65,536. Or I think that's the number. So when the result of a subtraction or comparison is lower than 0, so basically you need an extra bit to represent the results truly. If you truncate it, it's way off in this case. And then when the rotate shift operation shifts out a 1 bit. So basically this carry flag is set whenever you need that additional bit. Okay, so BCD flags. So these flags are used by the DAA instruction only and indicates whether the previous instruction has been a subtraction. H indicates carry for the lower 4 bits of the result. DAA, which is an instruction, and we'll go in detail about that later. Right now, we're just trying to get an overview of what we're looking at in terms of hardware, so that's fine. So DAA also uses the C flag, which must indicate carry for the upper 4 bits. After adding or subtracting 2 BCD numbers, DAA is used to convert the result to BCD format. So BCD, I think, is binary to decimal maybe. BCD numbers range from 00 to 99 in, I think this is hex rather than 00 to FF. Yep, indeed, $ means hex. Because only 2 flags C and H exist to indicate carryouts of BCD digits. DA is ineffective for 16-bit operations, okay, and used for increment and decrement. So inc and dec are common instructions for increment and decrement of numbers. Okay. Yeah. CPU flags and registers. Let's do this. Let's just briefly create a table for this. So CPU registers. CPU registers. Okay, so I think what I can do here is just copy this, paste it, and then have the LLM turn this into a markdown table. Turn this into a markdown table found in design.md. Okay. So I can tell it to either do it or I can just copy and paste it. So okay, so it's trying to do that now. That's great. This is easier for me to instead of just having to draw it. So pro tip right there. And let's see if it even becomes like a proper markdown table. So actually, let's just have it do it. Okay, do it for me. Do it for me in the document. So let's just act. Okay. Let's see if it changes it correctly. And remember, we're working with a small model here, only 30 billion parameters, but 3 billion active. And so far, we've been kind of productive with it. I mean, we made some progress in understanding the hardware better. Good news is that we don't have that many registers to learn. We just need to know that there's an AF, BC, DE, HL, and then the stack pointer and a program counter, at least for now. Okay. And keep in mind that this is running totally on my minis forum, X1 AI, AI X1 Pro. I need to name this correctly. What is this thing called? Minis forum, X1 AI Pro, AI X1 Pro, AI X1 Pro. Okay, so I'm really digging this PC right now, even though I'm kind of maxed out. But yeah, I did order more RAM, and not gonna tell you what kit yet, but definitely not the 128. So okay, it created a table. Let's save it, and it looks pretty good. So if we were to preview this, CPU registers are here. It looks like it added to it, so we can just get rid of the old stuff. So let's move this here. So duplicate. Okay, so cool. It noticed that there's some duplicate information. Let me clean this up by removing the redundant CPU register section that was already present in the document. Oh, that's great. Okay, maybe I should just have auto let it do that. Okay, save. Okay. We need this detail here though, as shown above, most registers can be accessed as either one 16-bit register or as two separate 8-bit registers. What that really means is that register A, for example, corresponds to the higher 8 bits of AF. Register B would be the higher 8 bits of BC. C would be the lower 8 bits, and so on. So it's kind of, if you mess with x86 before, you have like these AX registers, but then you have like AH and AL because that corresponds to like the higher 8 bits, lower 8 bits kind of thing. So it's the same concept here. So I would want this as like a caveat or at least like a tip. So let's do that. Okay, now flags registers. So flags register. And that is the lower 8 bits of the AF register. Lower 8 bits of AF register. So that has this here. And for now, let's just keep it like this. We don't need that much detail just yet. So let's have this model turn this into a markdown table and edit the documents with it to replace old stuff. Okay. So I'm giving it explicit directions to just replace the old one so it doesn't have to think so hard. So yeah. Okay, in the meantime, next is what? Next is going to be the instruction set. Now this is pretty important because this is the language of the CPU. These are all the instructions that that the Z80 supports and how we can actually tell the CPU to do things. Instructions, yeah. So what do we even have? So if you are looking for textual explanations of what each instruction does, please read GBZ80. If you want a compact reference card cheat sheets of each opcode. Okay, so what we need is opcodes. Why is that? Okay, this is great. Okay, hold on. didn't even turn it into a markdown table. What's up? Okay. So let me explain why opcodes are important. Okay. So if we take a look at a program is just a bunch of bytes in this case. And bytes is a number that ranges from 0 to 255. That's from 0, 0 to FF. Okay? Now, in your program, so let's say you have a program, or in this case, game, you have a bunch of bytes, and they all like are instructions for something. They can be like graphics, like literally bitmap graphics, or they can be like a loop or something, but they're all at the end of the day represented by bytes. So let's just say it's like 54, AF, CE, 3D, and so on. Okay, and this is as big as basically your entire program. Now, when your CPU executes, it fetches bytes in a queued fashion and executes them. And how does it execute really? Let's just say this. Keep it simple. It fetches one byte at a time, and it determines what to do with it. So let's say it encounters AF as the current instruction, like the current thing inside the pointed by the program counter. AF is the byte that's looking at right now. So we can think of this byte as what we call an opcode. So based off of this opcode, an opcode can map to an instruction, like an assembly instruction. Okay, so in this case, maybe AF corresponds to an add instruction. And depending on what kind of AF, it may tell us to look at next 2 bytes for the operators or the operands, right? Because this is the add operator, this corresponds to the add instructions, and then the next 2 bytes would be like CE and 3D. So it would be something like add CE 3D would be like the assembly instruction, and this result would get stored into, this is bad, the A register, for example, or the BC register, for example. That's why it's called accumulator, because by default the results go into some accumulator register. Okay, best I can explain right now. So what we need to do is we need to understand all the instructions available and their opcodes. So we're going to have to programmatically associate every opcode to a specific instruction. And then what we're going to do for an emulator is implement each instruction for the corresponding opcode. And we have to manipulate, we're basically in like this infinite for loop, pretty much going through fetching opcodes and then decoding them to the instructions, and then we're going to execute. That's basically the basic loop of a CPU. Fetches the opcode in memory up here, then it decodes it to find the right instruction. Based off of that, it's like a map. It's like a hard-coded map, right? And then it fetches the rest of the bytes, for example, like based off of what was the opcode, and then it executes to get the result. And you do that over and over again, writing to memory if needed, and then eventually you have a running program based off of that memory. So let's just say this, like this could, there could be like a store. Let's just say store instruction that stores to some address in VRAM with this specific value, right? So when we store the specific value into VRAM, we can think of this as like the screen, what is represented in the screen. This could be a color. So if we were to do this for 23,000 pixels, we could essentially draw a picture on the screen. Okay? That's how we would manipulate VRAM in this case, like conceptually. I would imagine that's the case for the Game Boy too. Okay, so let's save this resource here. And this is going to be where we're going to find all the instructions available, and we're going to dig for each of the opcodes. There's a lot of instructions, but we'll get through them. Okay, so that looks good. So far, we have used 21K of 65,000K context. Okay, making progress. Now, we want, so we're going to talk about the instruction set. So CPU, in this case, CPU instruction set. Okay, that could be its own sub. Yeah, could be its own sub section. CPU instruction set. In this case, all arithmetic and logic instructions that use register A as a destination can omit the destination, since it is assumed to be register A by default. So the following two lines have the same effect. You want to OR AB or OR B register. So again, A can be considered as the accumulator register. So any instruction that does stuff and operates on operands, results are stored in registered A unless otherwise stated in the instruction itself. So CPL instruction, I don't know what CPL is, but we'll find out. Can take an optional A destination, since it can only be register A. So this will be the same. So there are some instructions where it's only like a one liner kind of thing. I call it one liner. So when it's like this, it's assumed that any result is going to be in register A. Okay. Yeah, so let's learn a little bit about the notation here. So R8 means register 8 bits. So any of the 8-bit registers, R8 corresponds to any of these 8-bit ones here, A, B, C, D, E, H, L. Looking back at our table, A, B, C, D, E, H, L. So that's good. And then R16, 16-bit registers, any of the general purpose 16-bit registers, B, C, D, E, H, L. So B, C, D, E, H, L. Good. And then N8 is just the 8-bit integer constant, either signed or unsigned. So starting from -128 to maybe 127, or 0 to 255 in this case. And then you have N16, which is the 16-bit version of the integer constant. And then 8-bit signed offset is going to be called E8. And this is just notation for this book here, not like in the Game Boy itself. Okay. U3 is a 3-bit unsigned, I guess, integer in this case. So ranging from 0 to 7, probably used for flags and stuff. And then CC is the condition code, or this is the flags. So whether Z or NZ, okay. So NZ means execute if Z is not set, execute if Z is set, execute if C, which is going to be the carry flag, is set, execute if C is not set would be NC. And then vec would be like a function call. Think of it as a function call. We'll talk about that later. But anyway, instruction overview. So conceptually, we think about CPUs. CPUs are great at moving data, right? So CPUs in general are very good at moving data around. So we're talking about CPU moving data back and forth to RAM. So of course, minimally you would need load, store, instructions. Okay, so these are the two basic sources. You want to load data and you want to store data. That's what CPUs are very good at. Moving things around. They're good. They also calculate, but what do they do with those calculations? They have to move it to memory, right? And then if they want to calculate more things, they have to bring data from memory into the registers, calculate it, and then push it back to RAM. In this case, they can keep it in the registers temporarily, but it's not really. It doesn't make sense to try to keep it long term because other instructions would need those registers. Okay, so basically, we have these load instructions that will load, in this case, this one here, LDR8R8, means to load the value in the register on the right here, into the registers on the left. So, notation. LDR8R8 means load value to register on the right, from register on the right to register on the left. So in this case, R8R, R8L. So the steps are dereference or find value in R8R and store it in R8L. Okay? So LDR8R8 means to just, in this case, if we have LD, let's say E to B, so like this, it means to load value in E, put the value in, put that value, or let's just say store that value in B. As simple as that. So if E had, let's say, the value 120, then means to store 120 in B too, thus becoming B is 120. Okay, so that's I guess that's what it means. So that's why it says copy. So in the end of the day, E is still 120, but now B is also 120. So that's the notation. I just lost myself. Let's go back here. Okay. So in this case, we need to know cycles and bytes. So it's a 1 byte instruction, and it only takes 1 cycle to do this. Okay. Now I'm stuck in that. I don't know what the opcode of this is. Right? I was expecting to see what opcodes this would like correspond to. Let's see here. Do we have anything that would tell us that? Obsolete syntax, docs, vac. Let's see opcodes. Let's just search for opcodes. Opcode. No. Let's look for Game Boy CPU opcodes. Wow, we have a cheat sheet right there. Okay, this is a nice table and all, but that's really difficult to read. Opcodes table. Oh, another one. I want something like a list. Why can't we just get a list? I don't get it. I don't get why we can't get a list of things. It's like everyone likes to use a table. Is there a specific reason why? Why would there? Maybe we need to do more reading. Yeah, we probably have to do more reading because there is probably like a way to decipher this. Like the reason why there's probably like a pattern, like, oh, you know, if it's this type of instruction, of course, like this is what the opcode would be, is probably what I'm thinking. Okay, well, let's just try to learn this. So let's take the LDBB, for example. Are they really doing it for every combination like this? Is that the reason why? Oh, that's maybe the reason why. That's why it's 1 byte. Because if it is, I guess, a 4x40, I guess 40 would be LDBB. Let's actually ask the AI. What is the instruction for the Game Boy if the Game Boy CPU if the opcode is 0x40? What are we gonna get? Maybe we can read it like this. Okay, let's see. Come on. Ah, yes, we did read it right. Okay, cool. No, this is good. This is what I what I wanted to confirm. So 0x40 is 1 byte, and straightforwardly it just means to take the value in B and put it into B again. That's all it means. So if in memory we saw 41, it would mean take the value in C and put it into B in this case. So that's going to be the pattern. So let's pick something else. Like, for example, 9,4 is going to be sub H. So subtract maybe the value in H from A, most likely, and then we'll learn how to read these flags later. But let's ask what's 0x94 is the correct instruction. So how about the instruction corresponding to 0x94? Okay, so you're absolutely right about 0x40 being BB. For 0x94 be sub H, so 9,4 would be sub H. Okay, perfect. This thing is smart. Okay, great. Okay, so we have an approach. What I think we should do is we should document this correctly. This is very confusing. Let's actually document how to read this table, and then I think what we can do is we can take this and have the LLM convert this to like a JSON, for example, so we can maybe programmatically reference it in code. I think that's a good idea. Yeah, let's actually do that as like our first coding exercise with the LLM. Now that we know this could be a good guide to knowing all the opcodes, and that makes sense too because I'm assuming there are 256 different opcodes going from 0 to FF. We can confirm that with the AI model too. We can just ask that how many opcodes are in the Nintendo Game Boy instruction set, and then we can just copy this table into a file and ask it to generate a JSON with a few properties. Okay, so let's try that. Let's ask this question: how many different opcodes in total are there for the Nintendo Game Boy CPU? And my hope is that this table is enough. Okay, we're getting an answer now. Cool. 256 possible opcodes. All right, and not all of them are actually implemented. That's okay. Okay, many have variations with different bytes for operands. For our emulator implementation, we'll need to implement the complete instruction set that actually is used by Game Boy games. The most common approach is to create a disassembler or opcode table that maps to each opcode
or opcode prefix to its corresponding instruction. To properly document this and understand what we're implementing in our emulator, I should examine existing documentation files. All right, wait, no, that's fine. Let me create a file with the opcodes, and you can turn it into a markdown table. How's that? Okay, so now let's really test its ability to, I guess, see like this much context of data. So I'm going to copy this, and maybe it might be smart to make this a different text file itself. Okay, so that's going to look. Does that look like it makes sense? Let's see. Yeah, that does not look like it'll make sense at all. Or in fact, let's take a screenshot. Okay, now that we have this screenshot, let's save it and let's throw it to Quen again and have it parse everything out into JSON. Okay. Oh, we already have this, but let's just save this as opcode table. Okay. Now, what I'm going to do is I'm going to eject this model, and I'm going to load in a new chat a new model and pass this image in, and then have it decompose it into maybe a JSON, and then have it double check because it should be able to reference everything back. Okay, so for this, I think I had to crank up the context window. I may not have enough RAM, but let's just push it to the limit. So about 40K context for a total about 48 gigs of memory. I think this could be enough. So let's load the model and hope for the best. Okay, looks like we just barely squeaked by again. Okay, so we're able to load this 32 billion parameter model with a 48K or 40K context. So now I think we can at least drop in the picture and see what happens. So I don't even remember where I put the picture. Should have been somewhere. Okay, well I can just go back here. Oh, all files. Okay, so let's write our message. Here is a opcode table of the Game Boy CPU, Nintendo Game Boy CPU. The rows and columns correspond to the opcode number. For example, given some row such as 0x3, the columns correspond to the lowest order byte of that opcode. So in this case, 0x32, row 0x3, and column 0x2 corresponds to the, what was it? 0x or 3x, and then 2 is LDHL, comma A. Instruction. So let's get this right. Let's do 3x, and then row 3x, column would be x2, And then, let's see. Okay. To the LDHL. I don't know why it's minus, but oh, maybe it's like an indirect or whatever. Let's do 3x, 3x, something that's less confusing. 3x1. So SPD16. Let's do that. So 3x1. So in this case, opcode 3x, 0x31, and 3x and x1 corresponds to the LDSPD16 instruction. Now, right now we have notation. So here we can say, here is a reference as to what D16 and other notations mean. Okay, so D8 means immediate 8-bit data, D16 means immediate 16-bit data, and so on. Now, let's see here. This is going to be the key here. Okay, so the format for each cell in the table is, first, you're going to have the instruction, okay? The instruction, what is it? In this case, the length in bytes and the duration in cycles. So going up here, it's going to be 2 bytes, I guess. So LD, we knew that LDBB, for example, was 1 byte. That's true. Cycles would be, duration in cycles is 8. Is that so? Okay, so let's read this. Duration of conditional calls and returns is different when action is taken or not. This is indicated by 2 numbers separated by slash. Okay? The higher number on the left side of slash means duration of instruction when action is taken. The lower number on the right side means the duration of instruction when action is not taken. Okay, so that's probably for conditional. So if we look at the ones where they do have slash, they are probably conditional. So yeah, so when action is taken, it will be what? When higher number means the duration when action is taken. The lower number on the right side means the duration of the instruction when the action is not taken. Okay, so let's say if we're going to, so if it's not 0, we're going to do whatever this is, and that's going to take 12 cycles. Otherwise, we'll only need 8 cycles to process the instruction, and then this will be 2 bytes for the instruction. I didn't realize in this case, for example, this is 4 cycles, because when we read this somewhere else, it did say it was, in this case, 1 cycle. So that's really hard for me to understand, because this kind of contradicts everything. We'll see. So let's just say this. Let's just search LDBB. Okay, LDBB. How many cycles? So Game Boy CPU LDBB number of cycles. So in this case, an opcode fetch takes 4 clock cycles, takes 4 T cycles. Oh, which is equivalent to 1 machine cycle. Okay, and I think the T cycles goes back to this thing here, the CPU specifications, or not the CPU specifications, but the, what is it, hardware specifications right here. So there's a system clock, so that's probably 1 cycle for the system clock. Then master clock,
will be 4, maybe. So we'll learn. So yeah, T states. I don't know what that is, but they say that the 4-cycle alignment is correct. Okay, let's see how bad we'll screw ourselves over later. So let's take it as it is right now. I'm learning, you're learning. That's why we're doing it with AI, right? Okay, so the format for each cell of the table is first the instruction mnemonic. Is that how you spell it? The instruction mnemonic. Oh, mnemonic. Okay. So 1, the instruction mnemonic, for example, LDBB. 2, length in bytes, and then cycle T cycles. So in this case, example 1, 4, 3. This is going to be the flags affected. Flags affected. So for example, Z, NHC. NHC. We can just okay. So duration cycles. Okay, now let's give it a reference for flags. Okay, so reference for flags will be here. Okay, let's copy that in and have it just use that. Okay, so now your task, parse this table out and into a JSON object, 256 total elements with the following information. Instruction, opcode, what is it, length bytes, and then duration cycles, flags affected. Okay, so that's going to be our JSON structure, and let's just give it a little bit more hints. So instruction mnemonic. Okay, so that's going to be a string. The opcode in this case is also going to be a string. Or no, let's not do a string. Let's just do integer. Integer opcode. And then length in bytes is going to be integer. Enter length in bytes of instruction. And then the duration cycles is going to be integer duration cycles. And then finally, flags affected is going to be array of flags affected. Example, NHC. Okay, so that's going to be our JSON. And let's also have this one here where it's like note. Oops. Stop it. Okay. So then let's edit this and say, well, note for duration cycles. You may see a slash. Okay. You may see a slash. You may see a format of the duration cycles such as x/y. This is for the case of conditional opcodes where x is the number of cycles if action is taken and y is the number of cycles when action is not taken based on the evaluation of the condition. Okay, so let's say that and then let's do it again. Okay, now I think there's enough information. We'll see what the quality is. We'll check back. Okay, so this failed miserably. It was thinking and thinking for 71 minutes, and I think it was just so confused about the screenshot for the table. So I ended up just caving and ended up using ChatGPT, and even then it also struggled too. So I cleaned up the prompt a little bit, basically replaced with proper markdown tables, fixed some of my spelling mistakes and grammar, and also gave it better schema, like in a formatted way, and an example. And so it also struggled too. And this is with thinking on. It refused to do it with just from the screenshot alone. So it called a tool to search for the internet. And it did find like a data set that did have all this stuff already. And so it just started writing a Python script, and I started working with it to kind of polish up the data for it. And I realized that there was a flaw in that duration cycles could be X and Y, meaning that we should consider duration cycles where the actions taken versus not the actions taken. So there was an adjustment towards that I wanted to end up with. And in this case here, now I just had it give me the downloads to the JSON. So I want the exact schema in this case. I can just probably tell it to run the Python code. So yeah, let me just prompt that. Yes, generate the JSON for me with that script, please. And my hope is that it's going to give me back that JSON file with 256 entries. It's going to be a big one, but I want to use it for other purposes down the line, most likely to code gen. Yeah. As far as like code gen goes, we're going to write a few examples on how to implement each instruction. And so what really matters here is that we have an opcode, and based off of the opcode in like a switch statement, we'll fetch more bytes, and then we'll operate we'll like, for example, load. We'll just basically operate on the 2 bytes that we fetch. In this case, if it's 3 bytes, the first byte is going to be the instruction, and the next 2 are going to be the immediate value here. And we can operate on those 2 bytes and put it into the register. Essentially, that's what it is. And we'll keep track of cycles. We'll say, okay, after this instruction is done, we'll increment the total number of cycles so far to be 12 more. And we just keep doing that until we reached a certain number, and then that's considered like a second in time, for example. Yeah, it looks like it is struggling with this task too. I never expected it to be that difficult of a task. I thought it would be more simple than this. So yeah, well, again, we'll check back. Who would have known that this was going to be a hard task for any LLM? So I did more back and forth with Chat GPT, and eventually we got to the point where it's like, okay, I'm going to download the opcodes JSON from this GBDev website for you. Then you're going to write a script and run it, and you're going to parse out that data and then give it to me in the right structure, and then just let me download this JSON. So I download the JSON file, and it is what I want, but we're going to do a quick spot check. Okay, so I'm just going to choose opcode 159, and opcode 159 is going to be, in this case, 159 hex or 159 to hex is 9F.
So taking a look at 9F, in this case here, 9 F 9F is SBCAA. SBCAA length in bytes is 1, duration cycle is 4, and Z and H. And so let's see what we get here. Right? In this case, we have Z1HC and 1,4. So maybe this is not correct here. Maybe the flag Z1HC. In this case, Z1HC. Oh, that is correct. So N would be 1, but where's C in this case? So that's wrong already. So now we're going to have to fix that. At this point, I think what we can do is, looking back at this opcodes.json, it has flags in this way. So maybe we can just, yeah, you know what? Let's just do it ourselves. Let's have, yeah, you know what? Let's just have Quen Coder take these opcodes.json and then create a script that will parse it out into this type of schema. Looks like this is going to be a very difficult one for any LLM, unfortunately. So I gave up trying to do this, and instead I'm going to just use this opcodes.json directly. I'll just learn the format and just move on from this, because it seems like every LLM is having issues with just understanding what is actually going on. So we're going to have to use our brain power now. That's okay. And the answer's all here. We can just write simple scripts to I guess parse it out in the way that we want to, or code gen the way we want to. But what I want to define here in our design document is the difference between an unprefixed and I guess CB prefixed instruction. And maybe I should have done it this way. Oops. So I asked Quen on this question, and I haven't read the response yet, but let's hope that it is something that's helpful. So let's do this. Based on your request and reviewing the design.md file, I can now explain the difference between prefixed and unprefixed opcodes in the Game Boy CPU instruction set. Unprefixed versus prefixed. So in the Game Boy CPU, there are two categories of opcodes. Unprefixed opcodes. These are the standard 8-bit opcodes that make up the main instruction set. So they range from 00 to FF. So that's what we were trying to do all along, that one colorful table. So we know these are the sample instructions already. But there are also prefixed opcodes, and these opcodes that start with the byte CB. Okay, so that's true. After the prefix, there are additional 8-bit opcodes that represent extended instructions. This gives us an additional 256 opcodes for a total of 512 possible instruction codes. Examples include CB00, which is RLCB, rotate left through carry register B, 0xCB 0x37, set 0A, set bit 0 in register A. The prefix byte 0xCB, which now makes sense, is used to extend the instruction set without consuming additional space for the main opcode table. So whenever we're like executing a program and we're doing a fetch and then we see 0xCB as the current byte, we're going to have to look one more byte up to look at the real instruction to execute. So in our emulator implementation, you'll need to implement a decoder that checks if an opcode starts with the 0xCB. If it does, you'll use the second byte as an index into a prefix instruction set. If not, you'll use the first byte directly in the unprefixed instruction set. Okay, cool. What you just answered right now, can you update design.md design.md to reflect this information? preferably under the CPU instruction set section I had already attempted to define these terms, but you can do better. Okay, so I'll just have it do it on its own, and we'll see what happens. Okay, so it looks like it did something. I'm just going to save this and have it continue to do what it needs to do. Maybe it's done, but let's check it out so far. So I told it to edit. Oh, it's already done. So I told it to edit this documentation, and the definition of CB prefixed here is instructions that start with the prefix byte 0xCB. Good. Then followed by a second byte to determine the specific instructions. That's good. This extends the instruction set to provide additional operations like bit manipulation. Unprefixed, the standard 8-bit opcodes ranging from 0x00 to 0xFF that make up the main instruction set. Okay, so 2-byte decoding approach. Check if the current opcode is 0xCB. Okay, if yes, use the next byte as an index into the prefix instruction set. If no, use the current byte directly in the unprefixed instruction set. This allows for a total of 512 possible instructions, 256 unprefixed, plus 256 CB prefixed. Cool. Now, the next thing I want is I want to have a section that discusses how we're going to structurally use opcodes.json to generate opcode implementations. So CPU implementation, I brainstorm. Okay. So, let's just make this a new heading. CPU emulator has the following event loop. Is that what we call it? And this is in pseudocode. Okay. So while true, what we want to do is opcode obj is going to be fetch from opcode, or fetch, actually, while true, opcode goes fetch from PRG, from program. Okay, so we'll get the opcode object. This is object. It'll contain basically information on what opcode that we want based off of the current PC. So in this case, PC. And we can make it underscore, like private. And then based off of that, instruction is going to be, actually, opcode num is going to be opcode obj. And then that'll be something here. And then I guess if opcode num equals da da da, do stuff here. So implement the opcode. So that's like this is like the fetch right here, and this is the decode. So fetch, decode, and then execute. So that's like the loop, right? In this case, if opcode num starts with 0xCB, look to next byte to execute. Else, this is a normal one. Opcode num is going to be whatever we pulled. So next byte to execute, and assign that as opcode num. Okay, so let's have it polish that. Polish this up in design.md to take into consideration the fetch of 0xCB opcodes. Okay, let's see what it comes up with.
Okay, so it did stuff. um, it did it better than me, I guess. So, oh, it's still wanting to do more. Let's see. It better be good. And let's see how much context we've used. Okay, 28K, not bad. Okay, except. Okay, now CPU execution loop pseudocode. Is it done yet? Okay, great. Okay, so handle prefix versus unprefixed opcodes. If opcode obj0 is 0xCB, check if it's a prefixed opcode. Fair enough. For CB prefix instructions, we need to fetch the next byte. So opcode num is going to be opcode obj1. Okay, use the second byte as opcode. Great. And then for unprefixed, use first byte directly. And then opcode num equals opcode obj0, which is exactly what we want. And we'll have our implementation here. And then we can just clean this up because Quen did a better job than me. Great. So now we have to find what is prefixed and unprefixed. And now let's help out the model, like set it up to be able to read this opcodes.json so that it can start implementing like scaffolding the code. How we implement each opcode. Okay, like it's getting late. I've been like on and off on this the whole time, so let's just continue next time. Thanks.